Hello everyone, this is Emma, Ethel, and Jean, and our project is about the aortic heart valve. The aortic valve allows the blood to flow from the left ventricle of the heart to the aortic artery and prevents the blood from flowing backwards. Its function is important in providing regular blood flow to the rest of the body. A healthy aortic valve can become calcified over time due to calcium deposit buildup, which is known as calcification that causes the valve to be stiffer. High areas of stress within a calcified heart valve can lead to tissue failure. Here are pictures for a healthy trileaflet aortic valve and a calcified aortic valve. Notice that normal heart valves can have varying geometry between the leaflets, and usually no two leaflets are of the same size. Also, notice that the calcified deposits tend to occur in specific patterns. In this project, we will use a coaptation pattern, where calcification primarily occurs in the region closest to the wall and around the coaptation edge. The purpose of our project is to build a simulation model of a single leaflet of an ideal trileaflet valve using COMSOL and to compare the static stress and strain distribution on a healthy leaflet versus a calcified leaflet under diastolic pressure. Our hypothesis is that the stress remains the same because we assume the geometry of the valve doesn't change, and the strain becomes smaller for the calcified valve because it is stiffer. The result of our project would suggest a possible site of tissue failure, and it can be the first step to analyze the need of a prosthetic replacement for a patient. From previous studies, the ideal geometry of a single leaflet was based on elliptic paraboloid, and the function was used to model the bottom ventricular surface of the ideal leaflet. The coaptation surface, or edge of the leaflets that forms a seal with the edges of the other leaflets, was ignored when creating this model.
In order to identify the thickness of the leaflets, we decided to make a linear regression of the thickness of the leaflet as a function of its height, based off the thickness data provided on a topographic map of the leaflet. The thickness function was fitted to the general function of the equation, and this equation guided a lofted cut to create a shell with variable thickness. These equations for the bottom and top surface allowed us to build a model in SolidWorks. The right picture shows a cross-sectional view of the 3D model where it is apparent that the model contains variable thickness. The 3D model was transferred to COMSOL, where we assumed the diastolic aortic pressure to be 120 mm mercury with a ventricular pressure of 5 mm mercury. The wall face of the leaflet was held as fixed. The exact same geometry of the model would be used for the calcified model. However, the model was partitioned in such a way that calcification would occur from the edge of the wall to a fifth of the way down the length of the leaflet towards the center of the valve, and would also begin from the tip of the leaflet towards the wall edge and end in such a way that 75% area of the leaflet would be calcified, showing severe calcification of the leaflet. The healthy and calcified atrial valves that were represented as a linear material in diastolic phase can be seen in this first slide. For the healthy atrial valve, the stress was concentrated at the middle of the base of the attached side of the leaflet, as well as concentrated at the tip on the ventricular side of the leaflet that is touching the other leaflets. The maximum stress value was about 6.35 kilopascals at the tip location. The maximum displacement the valve undergoes at this time is 0.156 millimeters. For the calcified atrial valve, under the same conditions, the stress was concentrated in the bottom, towards the middle of the bottom calcified portion, between where the middle healthy region ends and the leaflet attaches on the ventricular side of the valve. The maximum stress value was about 42.9 kilopascals. The maximum displacement of the valve undergoes in this situation is 0.48 millimeters.
Now, on these next slides, you can see the healthy and calcified arterial valves under a lower pressure, which was a factor of 10 less than diastolic in this case, and they also had hyperelastic material properties. First off, for the healthy arterial valve, the stress is concentrated at the base of the attached side of the leaflet and the sides, all on the ventricular side of the leaflet. The maximum stress value was about 2.96 times 10 to the 4th pascals at the base and side locations, and the maximum displacement the valve undergoes in this situation is about 0.815 millimeters. Now secondly, for the calcified arterial valve, the stress is concentrated at the corners, where the calcified portion runs into the healthy valve portion of the upper calcified region, and is also seen in the bottom calcified region. It is seen on both the ventricular and arterial sides of the leaflet, and the maximum stress value was about 2.11 times 10 to the 5th pascals. The maximum displacement the valve undergoes in this situation is about 0.07 millimeters. To start, our group used general 2D bar models attached on one side to a wall that have the expected material properties to get a general idea of what we should expect. For the healthy valve, the displacement equation we ended up with shows that there would be a greater displacement in the healthy valve over the calcified valve as we had expected. Now let's look at the healthy and calcified arterial valves that were represented as a linear material in diastolic phase in the COMSOL model. The healthy valve had a smaller maximum stress, but it also had a smaller displacement compared to the calcified valve. This is not what we were really expecting to find, and future research could go into finding why this happened for our model. Lastly, let's look at the healthy and calcified arterial valves that were represented as hyperelastic material that experiences a lower pressure than diastolic by a factor of 10 in this case in the COMSOL model. The healthy valve had a smaller maximum stress and a significantly larger displacement than the calcified model, which was what we were expecting to see. However, we did try to make our COMSOL model as a hyperelastic material under diastolic pressure, but when we tried to do this, the equations did not converge. We found this limitation in COMSOL after trying multiple things to get around it. So we decided to do one model that has the diastolic pressure and one that has the hyperelastic material properties. This way we were able to simplify the equations enough that COMSOL could calculate the stress and displacement for all our models.